Good day, everyone. Welcome to lecture 5, is it, in the Materials Technology series. As you can see, we're going to talk about plastics, not the type of plastics that end up polluting our oceans, we hope, or we believe, but the sort of plastics that we can use in the construction industry. The terms that you're probably already familiar with are GRP and FRP, glass reinforced plastic, which is what it originally was patented as a material, and more recent terminology is fibre reinforced plastic, because the reinforcements can take a variety of forms. So it's not fiberglass. Fiberglass is one of the reinforcings that is used in FRP. Fiberglass gave the name glass reinforced plastic. So as you could, I've said to you before, I don't like to read from the screen, but I'll just read this one out anyway. As with any pouring or moulding process, the act of casting shapes out of fluid materials has the advantage that complex curved surfaces may be achieved. Large-scale structural components are now commonly manufactured out of resins that are reinforced with fiberglass. The fiberglass is built up in layers inside the liquid resin, process known as laminating, and products are often further reinforced with layers of foam, Kevlar or carbon fiber for extra stiffening. Now, we've come across laminating, of course, in other materials contexts. It is a way of stiffening materials, building up in layers rather than producing one solid. That in itself is interesting. So there are different kinds of fibers and there are different kinds of resins that are used in this process. Here are the fibers. E-glass, which as I said, that's what you would use have used the term fiberglass. There are modern synthetics such as aramid fibers and carbon fibers, and now more and more we try to use natural fibers such as hemp and jute, which as you probably know are also used to make rope. So these are materials that have tensile properties, and as I've said to you many times, and I'm sorry if I'm repeating myself, all the materials that we use in the construction process have to have compressive and tensile characteristics. Hence, concrete is reinforced with steel. Hence, resins are reinforced with fibers which can take the tensile loads. And hence, of course, timber is inherently a composite material consisting of fiber and resin. So the resins, polyesters, acrylics, vinyl esters, epoxy resins, phenolic, ceramic, and again natural or bio resins are all the matrices within which the fibers are laid up, which is the expression used in the industry. So there are two main ways in which we use fiber reinforced plastics in construction of objects, and of course one is to pull them through a die. It's sort of the opposite of extruding, where you're pushing, which we usually do with steel and aluminium, don't we? We push it through a die. With fiberglass products, I should just use the wrong term, haven't I? With fiber reinforced plastics, we tend to pull them through the die-shaped shapes that we require, and we end up with very similar shapes to those that we achieve with steel and aluminium. But as you can see, it's closer to aluminium in terms of the accuracy and of the sharpness of the edges that you can achieve with FRP. And of course we can pour all sorts of shapes and forms into molds, and we'll go into that process a little bit more. Here's some examples of what can be achieved just with plastics. And of course they are fantastically lightweight, and that's why we're interested in construction. We're interested because of the efficiency of transporting and assembling using FRP units. Ignore that. I will anyway. Um, so as we said, we can produce some very interesting and very complex forms. So the process is inherently composite in terms of design. You are producing the every case can be a one-off, if you like. Everything you design is bespoke, and this process of laminating or layering is critical to how the design is working as a structural object, as you can understand. It is a very specialist process, and we of course we're not asking you to particularly be a specialist, although you might like to attempt to produce some small components with this process. But suffice to say that the layering up of the tensile, whatever you use as a tensile material, as tensile fibers, will be directional. Okay, and you will cross laminate as you do with timber, and you will reinforce the product that you're designing as and where necessary. And of course, this can be analysed with computational fluid dynamics. I beg your pardon. Sorry, I've slightly lost the plot here, but I'll get back to you on it. What we're looking at is something that's often asked, which is, okay, you're making FRP sections, and you're then having to connect them together. With most materials, we already know a lot about connections and how we do it. With FRP, they are bonded; they're effectively glued together with adhesives, and you will miter those connections. So you're almost looking at kind of traditional sort of joinery, if you like, details in order to connect them together. The phrase I was looking for was finite element analysis. And more often than not, we need to thicken panels, and we need to make them. We tend to put them together as sandwich panels. So even though a traditional boat hull or car body made of fibre reinforced plastics will be composed of just the fibres and the resin laid up to a thickness of 10, 15 mil. To actually, what we do nowadays is build up these composite or sandwich panels, where we have the fibre reinforced plastic as sheets bonded either side of some kind of core. What you're looking at here is say a honeycomb aluminium core. It might be foam, it might be laser cut foam, which we'll look at a little bit. CNC cut foam we'll look at a little bit later on, where you can get sort of more complex shapes. But if you're making a simple flat panel, something like an aluminium honeycomb core will be very, very good. And of course, you can build these cores can be as deep as 20-30 mil, so you can end up getting a floor section out of a composite FRP and aluminium honeycomb core panel. Now we're looking at the detail of what you can do, and you're looking at a section through one of these panels. In this case, the core is foam, and therefore also is acting as an insulation, as you can see. And of course, you can design in all sorts of detail. And we're looking at what would look like a normal, you might imagine, to be a profiled metal sheet. So we're using that same principle of profiling a flat panel in order to give it stiffness and strength. This is fiberglass in its kind of the state that it usually arrives at in factories, in rolls or mats, ready-made to be laid up. This is the resin, the gel coat that's applied around it. And of course, it's a process of eventually of there's not been any paint applied to this product at the moment. You're literally polishing or shining up the surface of the final gel coat on the fiberglass. And yes, you can achieve an awful lot of detail. Far more than you certainly far more than you can with with most concrete products. So these are the foam cores around which most structural FRP components are made now. And as you can see again, these foam cores, well, these have not actually been laser cut. These have been simply cut on a bandsaw, and they will be skinned. What we're looking at here, if you're interested, is actually the fuel container for a yacht. Interestingly, again, people often ask, how do you connect? Okay, we're looking at connections again, aren't we? So if you manufactured an object like that, which you can in one go, and you want to connect it to another one, can you see what's going on here? Here's a steel connecting plate which has been bolted through into it, which allows you to, well, in this case, lift it, but also to connect it through to something else. So with FRP, we'll often find these kinds of metal connectors. So here's a few case studies. You might recognize this as a Zaha Hadid mobile or deployable pavilion. It was designed for Chanel, I think, I could be right, to display their wares in, and was to travel around the world. You'll see a little bit later on what we're looking at here is unfortunately not a structurally integral FRP plastic building. It's actually got a steel frame, although the designers of the skin, Optima Projects, David Kendall, who would be here talking to you today, sadly if it wasn't for the situation we're in, because he's a real expert and he brings in lots of wonderful samples for you to look at. David always says that it could have been. There's no reason at all why it couldn't have worked as a FRP shell, structural shell, without the steel reinforcing. The steel reinforcing was a product of the fact that it had to move around the world, and there were all sorts of different regulations, mainly fire, that it had to contend with, and it was just easier in the end to have a steel frame, and nobody worried about it. Anyway, so these complex shapes, these paneling, if you like, were achieved by initially taking large blocks of foam and CNC machining them, routing them to the appropriate shapes, onto which the resins and the fibers were laid up, or around which the resins and fibers were laid up, so that becomes a shell, if you like, if you want to call it that. There you can see the steel frame. You can begin to see how now, with just a little bit of stiffening, or with ribs, that these panels would begin to work as vaults. They could span. There's no reason at all why they wouldn't work structurally, but there you go. Interesting. So here they are mocking it up somewhere in the world. I'm not quite sure where. Clever, even the frame, of course. Steel frame was clever in so much as it's a bolt together frame, so it's easily unbolted and shipped off. You might want to think about this again when you're designing. You might be designing some kind of deployable structures that can deploy and be put out. You might look at this whole process. How do you stack and store the elements? Look at the kind of from cradle to grave sort of thing. How do you stack and store them when you're not using them? How efficient can that process be? How efficiently can they be put into position? There it is, as built. As an aside, and I don't think we've talked about it particularly, but the light. Natural light comes in through these panels, which are ETFE pillows. You might be familiar with the Eden Centre in the southwest of England, which is the big biodomes designed by Nicholas Grimshaw that are skinned completely in ETFE pillows. So what else do they make? Well, of course, you can make enormous single molds through this process of infusion molding, which I'm sorry that I'm not a specialist in, so I can't go into any great detail, but it's a sort of vacuum process. You suck out all the air and I won't pretend that I can go into it. What is interesting, though, is you really can achieve enormous single objects. Now again, when you're thinking about putting buildings together, and you might be thinking about using fibre reinforced plastics, of course this is a boat yard, so it's easy to move. You're going to push this out into a river or a sea which is near to you, so you can transport the object easily. So wouldn't you do that? You know, if you recall, I think when we were talking about aluminium, we talked about the Lord's Media Centre and how those monocoque sections were built by boat builders down on the River Thames and floated up the River Thames. That's what they do. Now you can achieve here, you're achieving a very, very large single spanning three-dimensional volume. I often look at this thing and I think, well, I'll turn it the other way up, and of course it's a roof, or it's a shed, it's a warehouse. It's fantastic, and it's all done in one go. So if you're near water, you can produce fibre reinforced plastics. It could be an interesting approach to putting buildings together. Of course, if you're building a yacht, you also have to have bulkheads to stop water. If it sprung a leak, the yacht will have a series of bulkheads that stiffen that hull and also stop there they go, they're coming in here, stiffening the hull and stopping if there's a leak anywhere. It prevents water flooding through the entire vessel. To be fair, this is one of the largest single fibre reinforced plastic castings that we know of. I think this was built down in Plymouth or Southampton on the south coast of England. If you can produce a 60-metre long mast, and the mast has to be an incredibly structurally efficient structure, you know, resisting the wind loads, has to be able to deflect, has to move a certain amount. Here's a funny little project, you may or may not be familiar with. This is by Lars Spoybrook of Knox Architecture. Lars was asked, this is quite old now, I would say it's a good 10 years old, possibly a little bit more. I know it was a competition, or I think he was actually asked to design some kind of beacon for a small town in Holland. And he wanted to do something that was fairly organic, so he designed what I think it was meant to be a heart or something like a heart. It's built from fibre reinforced plastics, as you can see. Actually, it's GRP, it's fiberglass reinforced resin. And just as an aside, the idea of this beacon was that it would glow, as you can see, and it would glow different colours. And the colour that it would glow in was selected by the residents of the town. Every day they would have to go online and type in how they were feeling. Happy, sad, medium, or something else. I think there were 4 colours in the end. Could be red, green, blue and orange, I'm not entirely sure. And so the whole town would feed in their general mood, and the thing would light up accordingly. And it might be people feeling very passionately red or slightly blue. As we know, blue means a bit down. So it's a kind of feedback loop, if you like, and a beacon. Rather nice idea. Only the Dutch could possibly want to have something like that in their town. And here's the finite element analysis of the structure, which is sort of Gothic. It's a vault again. It's basically a Gothic. It's a Gothic kind of structure, isn't it? And here's all the parts. Here's all the sections that were then bonded together as fibre reinforced plastic. What else could you have built it from? Because it still has that lovely translucency, doesn't it? Which is rather nice. Which is why it would have been fiberglass and not Kevlar or carbon fibre, which probably would have made it a lot less translucent. Here's a more recent project. Again, this roof was designed by a gentleman I mentioned earlier, David Kendall of Optima Projects. I will give you a link at the end of this to their website. And just while I remember, if you ask me, there are some web links to some quite interesting modern plastic processes, including weaving, carbon fiber weaving, which you can do with 2 7-axis robots, which you do have in our building. If you could convince the powers that be that that's what you want to do is weave carbon fiber with it, that would be great. So this is the roof that you're looking at. I know that this is only a virtual image, but the roof is completely FRP again. It started, as did the project, the Zaha project we were looking at previously, with these very large foam blocks, which are milled, routed into shape, into the shapes that were needed. Again, the beauty of the foam is, of course, that it can be shaped by the CNC machines, but also that it provides the depthness and the depth, the thickness that you need for spanning. It's also a natural insulator, as you know. So it's always doing these two things at once. So what we're actually designing here's the robot milling away at the surface. Here's the resin, the laying up of the resin and the fibers around that foam core. So the shape is gradually beginning to evolve. Here are the sections being moved onto site. Of course it's California, because what they're actually building here is a very, very large surfboard, aren't they? It's exactly the same technology. And here's the roof coming into position. It's pretty much uniformly cantilevering. You can see there's a little steel portal frame here. Some other things, quite nice things going on actually. Quite like this canted concrete. Concrete goes to steel. Steel goes to fiber reinforced plastic, which I think is really rather elegant. So there's the flying surfboard. Of course, one of the things you have to do with such a lightweight roof, and of course it is incredibly light, is this post here is not only supporting most of that cantilever, but it's also tying it down, because of course if you open windows here and any wind does get inside, it's going to want to take off. It's a great big aerofoil, isn't it? So what the current state of the world is such that the intention of the industry, of course, is to be able to design sections that can go farther for the smallest amount of material than anything we currently know. And this is probably true when we start looking at synthetic fibers like carbon fiber. Of course it's not entirely carbon fiber, this footbridge. There's resin involved as well. Look at the section. Of course it's a bit like a big box girder, isn't it? It's the same principle going on, box girder, but of course any shape that you like. The idea is that you will be able to span because of the lightness of the material. And of course this is an arch. It's an arch. I imagine it's part of an ellipse, and there are in one of your data sheets you will see that there are some clues about the best ways to span using pure geometric shapes. But I'll just quickly emphasize that if you cut sections through a cone, you'll find all the best shapes pretty much. So you will find ellipses, you will find the parabolic curves, of course you'll find the circle or semicircle, all of which work very, very well, we know structurally. I don't think you have the catenary curve, which is the other very, very useful curve, which I think you'll probably know from the work of Antoni Gaudi and others. You did the hanging chain, which you then flip, you mirror. It's a very efficient, becomes a very efficient structural arch. So you still, just what I'm emphasizing, I suppose, is that you still need to work with the pure structural principles of either arches or using, suspension or cable net structures to span large areas. This is something I kind of alluded to earlier on. This is weaving carbon fiber. This was an installation at the Victoria and Albert Museum a couple of years ago in London. I'm embarrassed that I can't remember the designers of this particular structure, but what we're looking at fundamentally is woven carbon fibre but also woven nylon mixed together, and these are then embedded in resin because they're not going to be stiff enough. The carbon is not a tensile structure. I have to emphasize this. It's not a kind of Friota. You can see there's no outliers. It's not a cable net or a suspension structure. It's not being pulled or pushed anywhere. It is mainly compressive, strangely, although it's made of lots of fibres. And I suppose in a way that's the beauty of it. You're using very light material to make a compressive structure, compression structure, aren't you? And I think this could be one of the last slides. I know this is a bit frivolous, and I know it's not architecture, but it is actually the state of the art in terms of a material, or at least a composition of a component that is made simply by the combination of using fiber reinforced plastics, in this case with air, so that the lightest things you possibly could, to achieve the stiffest and most structurally efficient shape. So I think what you're looking at could certainly be one of the futures of construction components. You can see there's a link to the website there. You might want to get in touch with these guys and say, come on, we can help me put some buildings together, or you may not. And finally, here's some links for now. As I said, if you email me, if you're really interested in this material, we've always got more references that we can give you. Optima Projects is David Kendall. He's very approachable. Again, if you want to email him directly and mention that you're students at University of Westminster, he will give you advice, I have no doubt. There's a National Composites Network and another similar group here. These are the two links that I said that are interesting because it goes to the very last that project I was showing you at the V&A, weaving carbon fibre as a structural material, which is the other future, I imagine, of this material in construction. So yes, there you go. Short but sweet, I hope. Thank you very much. See you next week.